Okay guys, let's study now some residual stress patterns. No? Before we are able to do the column strength curves, we need to understand how residual stress patterns are made. Okay? So residual stress patterns varies depending upon the process involved in manufacturing, and the common residual stress patterns are presented below. So for a more accurate consideration of residual stress patterns, it is of course recommendable, or it is recommended that we use standard shapes, because the processes involved in manufacturing are also standard. Thereby, the residual stresses may be accounted for more accurately than just fabricating the sections, uh, doing yeah, doing some procedures that are not standard, like in the manufacturing. Okay, so this is now a typical residual stress pattern for uh, a wide flange which is manufactured using standard processes. So if you will notice, the residual stress patterns are actually divided into the weak axis buckling. So what I mean by WABs, this is the weak axis buckling, and the SAB is the strong axis buckling. Okay, so we know for a fact that a buckling may occur either in the weak or in the strong side, depending upon the value of your slenderness ratio. And in this case here, the green pattern will be used for the weak axis, while the red pattern here will be used for the strong axis. Notice that for tensions, residual stresses, the assumed sign is positive, which is on top of the member element, and at the right side of the web element. So this is the flange element, and this is the web element. And for compressive residual stresses, we note that the sign convention is negative, which is actually at the bottom of the flange element, and at the left side of the web element. So this ABC here are actually different processes involved in manufacturing the white flange section, in which the first one is a hot rolled section, the second one is a welded, okay, welded white flange section, which is made up of universal mill plate, and the third one is a welded white flange section, which is made up of plates cut from flames. Okay, so the procedure are actually different, such that the standard, more or less the standard pattern for the residual stress are given here. And you will notice that the residual stresses are more controlled when you are using a hot rolled manufacturing process, rather than this welded manufacturing process. And also take note of the increase in the tension or residual stress when you are using a welded okay, welded process, and also the change in the stress type at the tip of the flanges when you are using a flame cut uh, wide flange section. So ang ibig sabihin ng flame cut, kinat itong mga plates using a flame, no? Pero ito pre-cut na to, no? So this is actually a plate which is already directly obtained from the mill. Okay, it's rolled plates. Ito rolled plates. Ito flame cut plates. Okay. So just take note of the difference. Of course, the values will be recommended by the mill uh, companies, or the milling companies, or the manufacturers. So for the test, no, how do they test this residual stress? They use an MTS 3000, or what you call a residual stress test method used by drilling hole into the plate elements. Okay, so the hole drilling strain gauge method is actually an ASTM E837 method, and the equipment they use now for advanced procedures is the MTS 3000. So I got this from the internet, and these are used by many companies and researchers to conduct some or to obtain some information on the residual stress pattern of different structural steel shapes and sections. Now take note that the residual stress is actually very much dependent on the cooling, okay, on the cooling procedure uh, rather than the heating procedure, although of course both affects the residual stress values and pattern, but still the process of cooling it is the one that is much more influencing in terms of the value of your residual stress. And we take note that in general, the rate of cooling, uh, when the rate of cooling is lower, then the tendency for the material particle at that point uh, will have a positive residual stress, or a tensile residual stress. Okay, so slow cooling, positive or tension, and fast cooling is negative or compression. Okay, so in this figure here, you will take note that the surfaces and the ends far away from the connection, okay, far away from the joints, are actually the fastest to cool, such that always have a what, a compressive stress, okay, at the tip of the flange and at the center of the web, while at the joint you have a tensile stress, because the joint tendency is to cool slower, except of course at this point in the flange for your flame cut welded wide flange, wherein there is a reversal in stress at this point from from negative to positive, since the assumption is that your flange plates and the web plates are actually cut using flame torches, okay, thereby increasing the temperature and making it much more slow to cool. Okay, so for the example here below, I want you to refer to Salman and Johnson for the complete solution, because was explained there very well, uh, using a manual calculation. So, but I did it instead of using a manual calculation. I want to present to you a MathCAD computation that will serve as your guide for programming in case you need it. Okay, so for the MathCAD computation, I will be explaining this on the separate video. So for now, I hope you understood how residual stress affects the initial stresses on the member component or the shape component, uh, as will be demonstrated to you by this example problem. Thank you very much.